Welcome back to another episode of Dave Does Math from Home. This might be the last episode of Dave Does Math from Home for a little while. I think this is it. We are finishing Calc 3. 17.8 is the last of this. We have mastered flux integrals and we've done the first shortcut, Stokes, where we can replace the flux of the curl with the line integral of the circulation. Divergence is the much easier shortcut for flux integrals, and after this, that's it. There's no more Calc 3, so excellent job. Divergence, the divergence theorem is a shortcut we're going to use to skip some sort of challenging flux integrals. And the divergence theorem says instead of doing the surface integral of f dot n ds, so this is your standard issue flux integral. Instead of the standard issue flux integral, we can do the triple integral of the divergence of f over the volume. So we all remember how to do triple integrals, triple volume integrals, in all kinds of different coordinate systems. That was the highlight of chapter 16. We were doing triple integrals in spherical coordinates, cylindrical coordinates, rectangular coordinates. We had all kinds of triple integrals under our belt. This theorem is going to let us skip doing a flux integral and instead do a volume integral. There are a couple conditions. The flux integral needs to be a closed surface. So when we did Stokes theorems, we had all of these things were open surfaces because we needed them to have an edge. So we were looking at like half spheres that had that circular edge around the top, and like paraboloids that had a circular edge around the bottom. Those things needed to be open so that they have those edges, those boundaries. For the divergence theorem, you can only use this on flux integrals that are closed, completely enclosed. So if you have the flux through an entire sphere, you can use the divergence theorem on that and replace the flux integral with the triple integral of a sphere. If you have something like a cube, cubes are really, really nice for the divergence theorem because if you're going to try and do the flux through the surface of a cube, you need to do 6 separate flux integrals because the cube has 6 distinct surfaces. Or instead of doing 6 different flux integrals, you could just do one volume integral using the divergence of the vector field. So that's the huge benefit that divergence has. And you can do it for other things too. You could do it for, if you were doing the flux through a paraboloid and also it's the disk base, or if you're doing a flux through like the 4 surfaces of a tetrahedron, like nestled into the origin. Like these are again examples where if you did the flux, you have multiple different surfaces creating this enclosed space. So you would have to do multiple different flux integrals. Or you can take the divergence of f and then just do a volume integral for the whole thing in one fell swoop. So it's a handy little trick. I did the homework for this section in about 6 minutes. I was able to do almost all of it in my head. It's nice. It's a good trick. It's a nice relaxing way, nice easy. We'll ease ourselves out of Calc 3. We're not gonna go out with a high stress section. We're gonna go out with a nice section that everyone likes. So let's start out with a relatively straightforward example. Find the flux of the explosion vector field x, y, z through a sphere of radius 4, centered at the origin. Okay, so hopefully we all remember the end of 17.6 where we did the flux through a half sphere, and the parameterization of that half sphere was horrifying, and doing the cross product of those partial derivatives took like 10 minutes. We're not going to do that again. We're just going to use the divergence theorem because we have a full sphere now. So it's an enclosed space. We can use the divergence theorem. We need to know the divergence of f. The divergence of f is the dot product of partial derivatives of this. So the partial derivative of this with respect to x is 1. Partial here with respect to y is 1. Partial here with respect to z is 1. So the divergence of f is a constant 3 everywhere all the time, which means that this flux integral is actually just going to be the triple integral of 3 dv. Now there's two ways we could do this. If you really, really enjoyed doing triple integrals in spherical coordinates, we could do that. We could set this whole thing up. This is going to be the triple integral. The function we're integrating is 3. dv is going to be rho squared sine of phi d rho d phi d theta. And then we got all our bounds. Rho is going to go from, what's radius 4? So rho is going to go from 0 to 4, and phi is going to go from 0 to pi, and theta is going to go from 0 to 2 pi. We could do this. If you're enthusiastic about doing triple integrals in spherical coordinates, we could make this happen. Or, if you're not enthusiastic about doing triple integrals in spherical coordinates, we could say that we're integrating a constant over a volume, and we're definitely going to get that constant times the volume, which is going to be that constant times the volume of a sphere is 4/3 pi r cubed, and r is 4, so these 3's cancel actually. So 4 pi times 4 cubed is 4 to the 4th, 256 pi. And that's it. We're done. I integrated nothing, but I know that the flux integral of this vector field through a sphere of radius 4 is this. A lot of the problems in this section are going to work out this way. Like you'll take your divergence and you'll get just a constant, and then it'll ask you for the flux through some surface, and you'll be like, okay, well, I'll just find the volume of that enclosed object and multiply that by the constant I get from the divergence, and then I'll be done. That's what I mean. I said I did most of this in my head. I can't do triple integrals in my head, but I can do basic volume equations in my head and then multiply them by constants. So this section is nice. I like it a lot. Let me do one more example of divergence things, and then I'll be done making videos for Calc 3. This is it, the last example. Let's go. This is the last one. I'm using blue. We're going out. We're going out in style. Where's that blue marker? Here we go. All right, blue. This is it. I want the divergence. No, I want the flux. Find the flux of f is x squared, y squared, z squared through the cube. 0 is less than, or we'll say the cube with vertices 0, 0, 0, and 2, 2, 2. So what we have here is a cube of side length 2. One corner is the origin and the other corner is hanging out in the first octave. And if we were going to do this one using a flux integral, we would need to parameterize all 6 sides of this cube, which honestly, those parameterizations wouldn't be too hard. Finding vectors that are perpendicular to the surfaces of a cube isn't that bad. It's just kind of annoying that we would have to do it 6 times. You know, the top surface of the cube, the normal vector is just 0i, 0j, 1k. And like the side version of the cube, that's just like 1i, 0j, 0k. So we could get those normal vectors intuitively without doing a bunch of cross products. But we would have to do 6 of them, and we would have to do 6 flux integrals with all the different top. It would be tiresome. Instead of all of that, I'm going to do the divergence of f. Divergence of f is 2x plus 2y plus 2z. And then I'm going to do the flux integral is the triple integral of the volume of this. So we're just going to do this triple integral, 2x plus 2y plus 2z, dx, dy, dz. Seems like a good order to do this in. And all of these things are going from 0 to 2. So let's see. First integral. I deliberately made this vector field be like actually interesting for this example. I think almost every vector field in the homework, once you take the divergence, it's just going to be a constant. And I didn't want only constant divergence to be the only exposure you had to this. So I wanted to do something with some variables involved at some point. So here we are. Integral of this with respect to x is going to be, these are still 0 to 2's. This one will be x squared plus x times 2y plus 2z from 0 to 2, 2y, 2z. So 4 plus 4y plus 4z. Okay. 0 to 2, 0 to 2, 4 plus 4y plus 4z, dy, dz. Let's bring this up over here and integrate with respect to y. That'll give us the integral from 0 to 2 of 4y plus 2y squared plus 4zy from 0 to 2 dz. So this will be 8 plus 8 plus 8z dz. I'm going to turn this into a 16. 16 plus 8z dz. So this last integral will give me 16z plus 4z squared from 0 to 2. Should be 32 plus 16 is 48. So in this example, we still did have to do some triple integrals, but it was a nice triple integral. After like most of a month of flux integrals and vector fields and weird nonsense, like coming back to triple integrals in rectangular coordinates with all constants for bounds is actually kind of refreshing, I think. So this is a nice throwback to triple integrals. It's good. Simple arithmetic gets you 48. You didn't have to deal with 6 different flux integrals through 6 different surfaces. So yeah, things are, this is good. I like this. That is the end of my examples for the divergence theorem. I hope you've enjoyed Calc 3.